Okay, hello, how are you? How are you doing? It's me, the pioneers in methods, the Professor Mourad Sultan Ezouidi. Today we have, let's say, a live session, okay, and we'll redefine the limits of algebra. Of course, we can say that today we have the honor to explore the breaking innovations in the field of algebra presented by Professor Mourad Sultan Ezouidi, a mathematician whose deep research of the polynomial equation has led to powerful new method solution. Contrary to the classical conclusions of Abel's theorem, which states that there is no general solution biological for polynomial of degree 5 or higher. Professor Ezouidi introduced a novel theoretical framework that allows the exact solution of specific high degree polynomial equation, including those of degree 11 and beyond, means 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and beyond. So using what's known as is really theorem, we we are going to solve the 11 degree polynomial equation. Welcome again to this first session, my professors, learners, colleagues, and teachers. Today, as we told, we are not just solving the polynomial equation, we are challenging mathematical history itself. According to Abel theorem, general solutions for 5 degree and higher polynomial are impossible using radical. The doors were closed. Mathematician stopped searching, but Professor Mourad Sultan Ezouidi says otherwise. Now we have new theory. Now we have a new method, new pathways that will give you exact, precise, exact rules. So, but Professor Mourad Sultan Ezouidi says otherwise. Through the power of his Ezouidi theorem, a new path is revealed, one that leads us beyond the classical limits into the exact algebraic solution of even the 11 degree from the equation. Today, I will demonstrate for you, my professors, learners, teachers, and colleagues, with no approximation, and not with guess work, but with precise exactness. As Abel says no, but Zudi says yes, it's solvable. Okay, so today we make history. I will snow. I will snow. Today we make history. I will show you two equations. Let's say I will show you one equation that exposes the failure of all classical methods, including Abel theorem, and reveal their exact roots using my own theorem, my own method that's called the theorem of Mourad Sultan Ezouidi. So our objective here, my professors, is to demonstrate the failure of classical algebraic method in solving certain high-degree polynomial equations and to introduce Zwicky theorem as a breakthrough that delivers exact symbolic solutions where tradition fails. And I will prove it right now. Okay. So now let me, my professors, guide you through the lens of Zwicky theorem when the structure and symmetry lead the way. In fact, it's not this is not trial or error and error. This is systematic. This is exact, and this is reproducible. So we are not say relying in my method. We are not relying on numerical roots. We are pulling the exact algebraic roots from the very fabric of thinking. So let's start. I will share the lecture with you. Okay, this is the lecture. I will share now the screen so we can see the 11 degree from the equation raised to the power, the equation that is raised to the power 11. Okay. Hi again, it's me, Mourad Sultan Ezouidi, from you professors and learners. I will guide you through the lens of the Ezouidi theorem where structure and symmetry lead the way. So let's start. Okay, this is our 11th degree polynomial equation that is written as x raised to the power 11 minus x raised to the power 10 plus 55 divided by 11 square times x raised to the power 9 minus 165 divided by 11 cubed times x to the power 8 plus 330 divided by 11 raised to the power 4 x to the power 7 minus 406 over 11 raised to the power 5 times x to the power 6 plus 456 times x to the power 5 divided by 11 raised to the power 6 minus 315 divided by 11 raised to the power 7 x to the power 4 plus 145 divided by 11 raised to the power 8 times x cubed minus 40 divided by 11 raised to the power 9 times x squared plus 17 divided by 11 raised to the power 10 times x minus 12 divided by 11 raised to the power 11 equals 0. So we can see this is our 11 degree equation. Apply any classical method, Abel's method, Newton method, approximation method, you will never find exact roots, and they will give you, let's say, wrong answer. Even I give this example to ChatGPT, and he did nothing. Okay, and he applied the theorem, and I helped him. I helped him find the roots. Also, DeepSeek, he didn't find the exact roots, and because DeepSeek is out of it's out of control, it cannot find out exact roots. Okay. So here you can see my professors. This is an 11 degree from equation. In order to solve this 11 degree from equation, we should first find the new 11 degree from equation. Okay, and we should determine the of this new 11 degree from equation that corresponds to the original 11 degree from equation. So these are the coefficients of my 11 degree from equation. L0 is 1, means L0 is equal to minus, between parentheses minus 1, which is positive. L1 is positive, 55 divided by 11 square, up to L0, L10, which is equal to negative, which is equal to negative, between parentheses, negative 12 divided by 11 raised to the power 11, which is 5. So these are the coefficients of my original equation. I will try to find the new coefficient related to the L subscript R minus 1 of 42, okay, applying the Ezouidi theorem, okay. So let's start, okay. This is Ezouidi theorem. This is the theorem of Mr. Mourad Sultan Ezouidi. This is the theorem of Mr. Mourad Sultan Ezouidi. Okay, let's dive into the structure, okay, or let's use or find the coefficients of the new 11 degree from equation that is written in terms of s subscript k minus 1 a of all the q's in the sum from 0 to k combination n minus r to k minus r and n to the power r between parentheses equal 0 to the q raised to the power k minus r times n k minus r to the q. Notes here, professors and learners and teachers and colleagues, that classical algebra halts here. It has no tools left, but Ezouidi theorem continues the journey. The classical road ends, in fact, with Abel theorem or with Abel barrier, but I've built a new bridge, and I will walk you across it now. Okay, so here I'm going to put k equals 0 in the theorem, and then find that s minus 1 is going to be equal to 0. Okay, here I mean s minus 1 is going to be equal to 0, to 1, sorry. And then let's dive into the structure again, and put k equals 0. We'll find that S0 is in fact the sum of the axes of this new revolution equation, which is again be equal to 0. So this is the formula for S0. Okay, is always 0. So here we just put substitution, and we find that the value of S1 is going to be S0 is going to be equal to another. We continue and dive again into the structure, and using the Ezouidi theorem, I will try to change this, okay, to yellow or blue. Yes, okay, it's good. So equal to obtain this one. Okay, after making our Vulcan, okay, and expanding and simplifying this formula, and write in its lowest term, this is S1 of order R for any n degree from the equation. Let's say it's generalized for generalized for any analytical equation. Means S1 in fact is the second second coefficient of this analytical equation, but n here is 11. So it's S1 is equal to negative combination into 1 times combination into 2 times 0 to 2 squared plus n squared times 4. What's needed now here, professors? We will just get replace L0 with 1 because here 1 and then 1 with 35 divided by 11 squared. So this one, in fact, is going to be equal to 0. So let's dive into the structure again, and you will see that every term is fixed and every coefficient has a message. Means what? Is 0 is equal to 0. Means the sum of lectures are going to be equal to 0. And also as one of the two is going to be 0. Let's say this professors and teachers and colleagues, this coefficient S1 or S0 or S subscript 1, in fact, are giving you a message. Okay. And it's really method knows how to listen. And let's say my target here is to let you also use this method, and um, I'm seeking for letting you know how to listen to this structure because it's not very easy and it's very difficult. Okay, so here you can see we call that I'm going to dive into the structure and use k equal 3 to find S2. Okay, let's dive into the structure again and from here. Okay, and we see that S2 in fact will equal to uh, S2 is equal to 0. Okay, after making the our substitution, we replace M0 with 1 and 1 with 55 divided by 11 and 2 with 165 divided by 11 cubed. We find that S2 is going to be equal to 0. Okay, so we continue and dive again into the structure. Okay, and you'll see the S4, S3, sorry. We are waiting for the Microsoft to be open. Okay, because that this is S2 is going to be equal to 0, my learners. Now I'm going to dive into again into the structure. 2k equals 4 will obtain the, the formula that will give you the fourth box of this 11-degree differential equation. Now I'm going to calculate or making substitution. I found that S3 equals to another. We continue and we want to find, let's say, S4. Just dive again into the structure and replace K with 5 to obtain S4. And you'll see that S4 here, my learners, my professors, my teachers, and my colleagues, S4 is going to be equal to minus 1. It's not equal to 0. Okay, means that S4, in fact, it's a coefficient. It's give you a message. Okay, y is equal to 0 and y is equal to minus 1 or 10 or so on. Okay, so now we continue and let's dive again into the structure. Every time it speaks, let's say every coefficient tells or has a message. Okay, and is really limited to know how to listen. So what seems impossible by tradition becomes now clear and exactly this method. Okay, my professors means that now I'm going to find the S5. S5 here, just I'm going to dive into the structure and put k equals 6, and I will reach the last one that is that has been written in its lowest term. I will make substitution and I find then I will find the value of S5 here is equal to 0. Okay, just calculation can do this using the scientific calculator. And now again go and dive into the structure again. Use the theorem and replace k with 7 to obtain S6, and we'll see that S6 here is equal to 0. And after let's say finding S7 and S8 and S9 and S10, then you are going to see how the roots will be clear and proceed and exact algebraic. Okay, so let's continue from that here, from that here. I'm going to replace k with 7 in the decimal in the theorem, and I'll obtain the last formula. Then I calculate 6. Okay, I'll obtain that 6 that is equal to an O. Now let's dive into again into the structure and to k equal 8 to obtain 7. This is the formula of 7. I'll come here a bit. That's how we can see the formula. This is the formula of the 7 when putting k equal 8. Then this one is written instead of 7, and we can just make the substitution of cells, and we find that the value of as as 7 is going to be equal to 0. It means that in fact we are redefining let's say the limits of algebra, meaning that the Professor Mourad can really explains how we can solve linear equations using his method. Okay, and this let's say pass bypass let's say Abel's theorem and the approximation method and Misaki method, because Misaki used guesswork. Okay, he supposed that for example alpha 1 equals 2 it's a root. If it works, he makes the let's say the first derivative and the process will continue. But at the end of the day, we give you let's say decimal number to even have an exact root and approximate it. So, okay, and here in this example we give exact roots. Okay, means that my learners here in this example, we give exactly. Okay, this is system, this is exact, and this is reproducible. Okay, so we are not in fact relying on numerical roots. We are pulling the exact integer roots from the very fabric of the number. Okay, so we call that, we summarize, we call that S0 is 0, S1 is 0, S2 is 0, S3 is 0, S4 is -1, S5 is 0, S6 is 0, S7 is 0, S8 is going to be 0. Okay, this is S7, S8 also has to be equal to 0. Now let's dive into the structure, or let's use the zero theorem, and the Professor Mourad Sultan explains that S8 is equal to this formula that has been derived from the zero theorem when putting k into mind. So this is the formula. Just now I'm going to substitute, and I will find that the value of S8 is going to be equal to 9. Okay, K8 is not guessing, not approximation, not approximate, sorry, but exact. We see that we indeed redefine the limits of algebra. There is nothing that say if Abel say no, Mourad open the door, and Mourad tells you, yeah, we have a new method, new theorem that will get you in in the field of exactness. Okay, with no approximate limits or what guesswork. Okay, or what can you say? Mm-hmm. Can you not guess it, not approximate it, but just everything is true. Okay. So here, Ezouidi, Mourad Sultan Ezouidi Mourad Sultan apply his theorem and his method, and he told you that this is the value of S8 is going to be equal to an. Now we are going to dive into the structure the professors teachers, colleagues, and my learners to dive into the structure and in case they can to obtain this now. So here, as you see, we are now diving into the structure and trying to find the value of S9, okay, using the method of Mourad. Okay, so here, when, okay, here, uh, if you watch closely, those will emerge one by one. Each step that is justified. Okay. So here, because that I'm going to find the S9, I'm going to put K equal 10 in the Zwidy theorem, and Mourad Sultan Ezouidi explained that, let's say, uh, let's say that S9 is equal to 12. Okay. We see that before that S4 is equal to -1, isn't it? Now S9 is gonna be equal to 12. Okay, so you can use a calculator and okay, or I will do this for you. Okay, or you can do it okay by yourself and calculate this. You will find that it's gonna be equal to 12. We continue. This is a simple calculation. Okay, we continue my learners. We call that okay. We call that S9 is gonna be equal to 12. Different with it. And this one, when telling that S9 is not equal to 0, means that uh, each or every time it skips, like means S9 is supposed to have it's speaking to you, okay, it's telling you a message, okay, and each coefficient has a message impact, okay, and what else? And is really method knows how to listen. Okay, so we continue now and go to dive into the structure again and to page 11, and I will tell you, or I will let's say uh, this will imply that S10 equal to negative to combination 10 to 1 times combination n to the 11 times 0.2 to the power 10. Okay, of course. This is S10, yes. So this is L042 raised to the power 11. Okay, this is to the power 11. Okay, then n minus 2 will give you 9. Okay, like that. Now I apply up to n raised to the power 11 times L042. This is the formula has been generalized and simplified and written in its lowest term. Okay, after diving into the structure and frequency to the 11 is obtained the 11th the 11th of the new replication equation. That corresponds to the original replication equation, where the coefficient of the original replication equation are x1 plus 5 by 11 squared up to 12 divided by 11 and to the power 11. Okay, here now if you watch closely, we will write your replication equation in terms of S subscript 10 minus 1 of order R. Then you are going to solve this new replication equation and go back to write alpha subscript K from 0 to K, or K to K dash equal plus the new options of this new equation. Divide by n is 11, and everything will be obvious to you to work across. Okay, so here as you see my professors and those who have smart minds, those who believe in mathematical researchers. Okay, this is in fact the so we told now we calculate S10 here. S10 is going to be equal to now I'm going to say, in other words, let's say what seems a possible calculation becomes more clear and exactly exactly that possible. Okay, watch closely and let's say the coefficient of the new representation equation uh, will emerge one by one, okay, and you see that our 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 new representation equation has to look like that. X equals to 11 minus 0, x equals to 10 plus s1, x equals to 9 minus s2, x equals to 8 plus s3, x equals to 7 minus s4, x equals to 6 plus s5, x raised to the power 5 minus s6 for the x raised to the power 4 plus s7 for the x cubed minus s8 for the x squared plus s9 x minus s10 equals 0. You see now the coefficient of the new replication equation of k are written like that, and just you would put s4 is minus 1, you put 0, and s9 is equal to 12. You are going to write it here, okay? This is meaning that x11 minus s4 for the x6 plus s9 for the times x equal 0. We can see that x equals 0, it's clear. Means s10 here is equal to 0, means the first thing is it's clear. Just put a 0 for that to divide by n, okay? Because the first x is going to be equal to 0. Now, this is it's a quadratic equation. So in fact, it's a 10th degree equation, but it's written in second degree equation with capital X equal small x, is to the power 5, all squared minus s4, alternative small x raised to the power 5, all is equal to 1 plus s9. Now I will use my discrete formula. Okay, I'm going to find the coefficient of the second degree equation relative to the origin second degree equation when putting capital X equal to small x raised to the power 5. That will be a negative s4 squared plus 4 times s9. This, in fact, is the second property of the new second Newton equation. That's why here, if you calculate this, you will find that it's positive. Okay, negative 1 plus 47 is positive. This is the coefficient of the new second Newton equation of the x course. So now, when putting x squared plus s1 of 42 dash equals 0 means x squared is equal to negative s1 of 42 because this is positive Newton square on the right hand side, so it will be negative s1 of all the two dash. That's why we wrote it as negative s1 of all the two dash equal negative 37, which is negative how we get the complex roots here. Okay, so let's continue. Okay, let's continue my learners. Okay, so here my teachers, if you watch closely or watch closely the roots with more one by one, it's step perfectly justified. So I want to make p of x subscription equal of course p of differential x going to be equal to whatsoever the value of k. So here, because this is negative now, I'm going to write x equal to power 5 equal s4, okay, plus root of negative s1 for the two that divided by 2. Therefore, I will obtain the first step complex number, which is x subscript k from 0 to 4 is s2 plus negative root of negative s1 for 2 raised to the power 4 divided by 2, okay, all the way to the power exponential 2ik times over 5. Or now I'm going to change the square root minus 1 to be negative s1 for 2 is 45, 47i times I becomes negative divided by 2 raised to the power f exponential 2k plus 1 2k 2ik pi divided by what? Divided by 5. Now I will obtain in fact the first 10th complex. Okay, so or the fifth conjugate complex numbers. Okay, here watch closely and go to the one by one. Okay, means this is the main application, and you see that the zero theorem is not only powerful, it will how to say stop here to better. So stop here before we start. And here, go down. Okay, here. Now, just a moment. So, means that the x subscript k from 0 to 4 is equal to negative 1 plus 27 raised to the power half times I divided by 2 raised to the power 1/5 raised to ik pi divided by 5. So this one, in fact, is written as 1 minus 47i exponential 2 2k plus 1 I pi divided by 5 minutes. This thing can be written as that 1 minus 47 times I over raised to the power 2 or raised to the power 5 exponential 2k plus 1 I pi divided by 5. Why we add the 1? Because this is a minus 1 I write minus 1 and minus 1 is to the power 1 over 5 is execute exponential I pi divided by 5. Everything same denominator, then I'm going to add the numerators together like that. So we see the first 5 x roots of the going to the power 11 means this one just 1 minute, outcome 0 is possible. Okay, we see this one stop here. So these fifth, uh, these five, these first 5 roots are the roots of this polynomial, okay, to the power 11, okay? And also here, the other five roots also can be written as -1, -7, raised to the power half times I divided by 2 all raised to the power 5. Explanation 2I divided by 5. I will put -1 as explanation I pi raised to the power of 6 means explanation I pi divided by 5. Then I'm going to put here, and I have same base I should add the indices. I have same denominator, so I should add the denominators. So this one to be 1 plus 57I divided by 2 over 1 fifth. Explanation 2 plus 1 I pi divided by 5. So these are the 10 exactors, okay? The 10 exactors. And uh, and so one by one, the examples of this little equations tend to be before us. Okay, where others, so all we have covered very well. We have covered very well. So this proof not the others because that there is more beyond the secondary. The theorem does not break rules, it reveals the deeper structure behind them. Okay. So now as we find, let's say, the 11th degree from the equation of this new evolution equation, we are going to write, going back and write the roots, the exact roots of the original evolution of the equation. You can see here, you can see here, you can see here, okay, that we are not around, we are within, okay, and what else? And here it is, not guess it, not approximated, but exact, everything is right. And what else? Yes, just a moment, I will go. Mhm. And in the future, we'll solve also 12 degree equation, 13 degree from the equation, 14 degree from the equation. Okay, so here we come back to see the exact roots of my original from equation is written as a 0 plus subscript from 0 to 9 divided by 11, which is equal as 0 is 1, I put here 1 plus 1 plus root of 47 times I divided by 2 raised to the power 1 fifth explanation 2k plus 1 I pi divided by 5 all divided by because this is n. Or I'll subscript from 0 to 4 will be 0 plus x subscript from 0 to 4 of course here, okay? Uh, equal 1 plus equal 1 plus in between parentheses 1 minus 47 root of I divided by 2 okay raised to the power exponential 2k plus 1 I divided by 5 or alpha k 11 or alpha 11 because before the new evolution equation has x equals the original child going to 1 plus 0 alpha 11 equals 1 alpha 11. So here my learners the exact roots. Let's say yes. Okay, what shows the roots in the one each step perfectly specified. Now if I going to put all these roots inside your original definition equation, your equation will be satisfied. Okay, and you will perfectly and each step perfectly satisfied. Okay, now thank you for listening. Thank you for listening, my learners. This is Mourad Sultan Ezouidi, the pioneer in methods was with you. Okay, so how to say it here? Okay, so let's say, and so one by one the exact proofs of this 11 equation stands before us, where others, so all we have carved other way. It's proof not that Abel was wrong, but there is more beyond the boundary we describe. It really does not break rules, it reveals the deep the deeper structure behind them. Thank you for joining. And remember, mathematics still holds secret, but we, as Professor Watson, really hold the key. Holds the key. If the classical algebra fails to find these roots, and yet they are here, explicit and exact, then it's not the equation that is insolvable, but the method that is absolute, absolute, absolute. But the method that is at means has has no sense. Abs- Absolute. Okay, I will just check the pronunciation of this word, then I will pronounce it. Absolute. Absolute. Okay, let's see. Absolute. 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 But the method that is absolute. But the method that is absolute. Let's see. Let's what some what's it. So Abel says no. Abel says or said no formula exists today. I say here it is. So as a conclusion, Ezouidi theorem is not is not just a breakthrough. It defines what is possible in algebra. Where a classical theory fails, this method reveals truth through exact sample solution. So the frontier once closed by Abel and Galois, and Galois has now been opened. So Professor Mourad Sultan Ezouidi, inventor of Ezouidi theorem, contributing authors in research in sample algebra, author of mastering the resolution of 10, 9, and 76 fifth, fourth degree from the equation, solving also sixth and fifth degree from the equation using the Euclidean theorem, exact solution of fourth degree from the equation beyond classical method. Okay, also I published another book, okay, in Dutch edition and French edition. The theorem and proposition, degree N residue part researcher to general study. So these works lay the foundation of a new era in mathematics. We are solving high degree from equation. Is no longer the exception, but the standard. Okay, thank you and goodbye. This is Mourad Sultan Ezouidi, the professor. Mourad Sultan Ezouidi explained for you how classical method does didn't and faith, okay, and his method and how his method works to solve 11-degree polynomial equation, okay, with exact roots. It's not easy, and we hope so that you got the point. Okay, okay. Thank you for listening. This is me, Murat Sultan, the professor of mathematics. Soon I will be online and I'll be live with you another examples. Okay, thank you and